So my line that I take on it is that all of the technical glitches that could have happened with the telescope got transported onto the live stream. So you had to have them at some point. So better to have them there than on the telescope.
That's right.
So I think we'll probably go with that one.
I like it. Yep.
What's up, you scholars of enlightenment? Dr. Sam Gregson here again. I hope you've had a wonderful day on this fantastic, historic, milestone day for science. Today and yesterday, NASA released its first full-color images and spectroscopic data from the James Webb Space Telescope. And I think it's fair to say that scientists around the world are pretty excited about them. The release represents the first wave of full-color scientific images and spectra the observatory has gathered, and the official beginning of Webb's general science operations. Today, we will be discussing those images with Dr. Michelle Thaller. Dr. Thaller is an American astronomer and research scientist and the Assistant Director for Science Communication at NASA's Goddard Space Flight Center. She is also a frequent on-camera contributor to programming on the History Channel and the Science Channel. She was also front and center during today's NASA live stream, where the James Webb Space Telescope images were revealed to the world. Please enjoy this fascinating conversation. Right, so I would love to chat through these images with you if you're game to do so.
I am. I think it's at some point, like in the next half an hour, there's going to be a pizza that arrives at the door, but I think that would add for some local color.
I am more than happy for you to eat pizza while we discuss it. This is
and you can see my cat, who's not very interested in this whole thing. That's right. But anyway, yes, I'm here to discuss the imames.
This is absolutely not a problem. And I know you've had a very busy day, so as soon as I get boring or you've had enough, please tell me that's the end of today's session. So I think the first place we have to go, and it would be remiss, even rude of me not to, is to ask you your general reactions on seeing those images today. How do you react to them?
Oh yeah, I mean, it's. I guess the first time I saw the images was probably last Thursday, and that was when we were starting, rehearsals for the show and all of that. And so, I mean, I think I had the same reactions a lot of people had, but there's a little bit of a nuance here because, I got some people saying, well, hey, these don't look the same as, giant mosaics that Hubble took that took months to make. And it's that's kind of the point. So all of these observations were done quickly.
Yeah.
I mean, there was a lot of pressure saying, we really want to see the first data from the telescope. We want to make sure everything's working. And so the images that we put out are things, I mean, you heard, one of the scientists today, Jane Rigby, say this is sort of the stuff that we did before lunch.
Yeah.
I mean, these were exposures that were a couple hours long.
Yeah.
And the thing that, I think that a lot of people in the public might not appreciate is that, we were getting deeper information in the universe, farther away stuff than Hubble had been able to produce in weeks of doing the same observation. And it was just like, bam, it was just there. And so, for us as astrophysicists, we were sort of like, it's that good. It goes that fast.
Yeah.
I mean, you want to know what chemistry is in an exoplanet's atmosphere. Bam.
Yeah,
I mean, these are fast observations. And like the things like the Carina Nebula, right? That was just a tiny little bit of the Carina Nebula. I mean, someday we're going to produce a gorgeous big mosaic of a whole stupid Carina Nebula, but this is just, I'm going to have to clean up my language for being in the public here.
No, it's okay. We don't worry about that on this channel. We're fine.
Okay, someday we're going to produce an image of the whole fucking Carina Nebula. But, I mean, this was just a little bit that we did right away, and you can already see structures in there and stars in there we've never seen before. Huge success. I mean, wow.
That's what really struck me as somebody watching and someone who knows, a little bit, not too much, but a little bit about how JWST works. It came off to me as a really, really successful tech demo, right? You have this new telescope in a new wavelength regime, a new way of putting telescopes together, unfurling it in space, and you had images that showed that it can look further back than we've ever looked before. It can take the spectra, it can take transits, it can, do all of these things, look through the dust and there seemed to be no problem. The data seems to be coming quickly, it seems to be coming cleanly, and essentially JWST seems to be open for business on all of those kind of, those 4 big points that it wants to aim at: galaxy formation, interaction, looking back as far as we can into the early universe, stellar birth and death, and then exoplanets. Those, you'll be able to tell me the answer to this question, but how were those images selected? Were they selected sort of by committee to make sure that we could see that all of these main themes were being hit?
Well, absolutely. I mean, so we had more than these 5 to choose from.
Right.
And I mean, as we speak, the telescope is still observing and it's producing gorgeous images. They're just coming down. And
I'm really
so
annoyed that I can't see the discarded images now. Like,
I know. I believe, and don't absolutely quote me on this, but we're going to have another image release on Thursday.
Yeah.
So in just a couple of days, my guess, this is a decision above my pay grade, but my guess is that some of the images that we didn't use for the broadcast today, you'll probably end up seeing. I mean, that's what I'm hoping to see. But yeah. So not only were they decided by committee, but they were also decided to give each of our international partners something to really showcase.
Yeah.
So, for example, we had this result of the exoplanet spectrum that we specifically wanted to have Canada do, but then Canada had some technical problems with their video feed. But the whole idea was, the instrument that did that, the near infrared spectrograph, was that was a Canadian contribution, and and then same thing with the Europeans. We wanted to talk, so it was done with 3 different space agencies.
Yeah.
Interestingly enough, not a whole lot of input from either the science team on Webb or even the communication people. This was sort of more decided kind of at a political level, which, it's fine. We got plenty of images. You're eventually going to see them all. Yeah.
Talking of politics, the first image that we saw kind of came out, and this, I'm just going to do a little bit of background before we see the beautiful image. The first image we saw was of SMACS 0723, which is this galaxy cluster, and President Biden got a little sneak peek when he finally decided to show it after he was very suspenseful about it and kept us waiting for a while. But so I guess this just goes to show, before we even get into the images, and you made a really good point of this on the stream today at NASA, that this is sort of the world's telescope compared to the things that we're looking at that are so far out. It doesn't matter if we're in England or the US. This is our telescope, because relative to these things so far out, we're basically all in the same place. So it's something we can all share in and feel small looking at the grandeur of the universe, right? And I guess that's where the politics comes in, and people wanted to talk about that, how it brings us together.
Absolutely. I think everybody's hungry for some good news right now. Yeah. I mean, it's certainly been a tough time news cycle wise. It's the world's telescope in more than just a metaphor, though. I think that sometimes, sometimes I still get questions where people say, it's like, so when will NASA let us see the data? It's not NASA's data. I mean, so for one thing, there's 3 major space agencies that are contributing, but there are countless scientists around the world that have already won time to use this telescope. This is a public observatory, right? So the way, the way this happens is anybody with a PhD in science can write in and propose, every year there'll be a proposal cycle. I would like to look at this object. There'll be an international panel of scientists that will then decide which science projects they'll give priority to. So, I mean, this is a telescope people in India will be using, people in Africa will be using, people all over the world. And, and specifically, Canada, the United States, and the European Space Agency, all those taxpayers, their money went into creating this incredible, asset for humanity. So this is everybody's telescope. This is a public observatory.
It kind of reminds me of like CERN. CERN is really the UK's laboratory for doing particle physics, but it happens to be in Geneva, in France and Switzerland. But that's where we go to do our particle physics.
Absolutely. And there are people that's working at CERN that are from the United States, and there are contributions from the National Science Foundation. I mean,
Yeah.
to support research. I mean, these things are big international projects. And, when we first did the Webb launch, we actually were very careful not even to have like NASA logo pins
Yeah.
because, Webb is an international mission. It's not just a NASA mission.
Amazing. It's a really nice sentiment. So let's get into some of these images. So the first one we saw was this. Exactly. So SMACS. Am I allowed to say SMACS or do I have to say SMACS?
So, I always say SMACS, and the same thing with the exoplanet. I always say WASP, 96B. So yeah, let's do it that way. So I have to say, so this had us scurrying yesterday. We were expecting to release these all during the press briefing today.
Yeah.
And then we got a call from the White House saying that they wanted to do one. And of course, I mean, this gave us a tremendous boost in the news and publicity.
Yeah, amazing.
I mean, it was, we were all kind of like, what do we do? So this one was going to be sort of our big kind of finale, but it also is very fitting to be the first one that was released because this is spectacular. And once again, you have to understand that this was just done in a couple of hours. A similar field to Hubble took 2 weeks.
So this is I believe the Hubble image, and this took.
Oh, you got it up Hubble.
Yeah,
right,
I think so. So this, can you see? So this is, I think, took 11.
The image on my screen's a little small. So
that's all right. That's not your fault. So it took, I think, 11.5 days, which because Hubble orbits could have been like 25 days of telescope time. And this is, maybe you want to tell people a little bit about what is this SMACS 0723, and then we'll look at the beautiful new image that's come
Absolutely,
through from Webb.
yeah. So this is one of the best examples we have of a natural telescope created by bent space itself. I mean, so 100 years ago, I mean, Albert Einstein, I don't think he ever thought we would actually see this.
Yeah.
But Albert Einstein told us that what gravity really is a bending of space. I mean, it's weird to think that, but that, he said that's really what's going on. Space itself is bending. And, I mean, Einstein died before we ever had a chance to actually see, take a picture that was true. And so what you see in this image is that there's a bunch of blobby looking, in this image, white galaxies. And the bigger ones are kind of closer to us. We see them as they were about 5 billion years ago. And then behind these big galaxies, what's going on is that the galaxies themselves and all of the dark matter, all this, missing mass that makes up most of the mass of that cluster of galaxies, it's actually bending space into a natural telescope. And we've learned how to use this. I mean, it's a wonderful gift to us from the universe that, although the image of the galaxies behind are distorted, they're actually boosted and focused and brightened by this gravitational lens. And so because the galaxies behind are normal, regularly shaped galaxies, but their images are smeared out into arcs and all these weird kind of distorted mirror image of it. I mean, it's just lovely. And but that's real. That's not created by a computer. That's not some kind of model. If you had eyes, in this case, as sensitive as the Hubble, you'd see that. And I mean, that's really what the sky looks like. But so the weird distorted things are the things that are just these, again, they're just wonderful things to pick out of the universe, because these are things that are so far away we wouldn't have been able to see them without that gravitational lens. And wonderful stuff. So that's a gravitational lens, a bunch of fairly nearby galaxies, only 5 billion years old, as we see them, are lensing galaxies now that we know that are over, 13 billion. The light is 13 billion years old.
So what I find so amazing about this is going from the Hubble image here, which is already amazing, and then going to the Webb image.
Yeah, it goes much deeper.
I mean, it just goes so much deeper. You see so much stuff pop out. So for people watching, you can kind of overlap these a little bit in your mind. You can see the bright star, the sort of Beret galaxy and the 3, and you can see those when we shift over here, the large star, the Beret, and the 3 sort of rotated on its side. But look how much other stuff just pops out, because you can. I guess this is a function of being able to look in the infrared, so you can look back to higher redshifts, so further back in time. Also being able to collect more light. And you said they did this in a day?
6 hours, half a day. So, I mean, we can do, a couple of these a day. And I mean, unlike Hubble, Hubble is, orbiting around the Earth. So, Hubble always has to interrupt its observations because, the Earth gets in the way as it's orbiting around. The Webb isn't orbiting the Earth. It's out by way past the moon, 1 million miles away. So it can just stare at this thing. And, this is what you get with just a sort of a quick snapshot. So what happens when we do 2 weeks on this?
I was just right. So this is what everyone was asking on the stream today was what the hell happens if we do like for like with the Hubble image of 2 weeks or whatever it is, or 11 days? What would the Webb image look like? Which I guess we'll find out eventually. But is there any space that's space anymore, or is it just rammed with light? What's that going to look like?
Well, so absolutely. That's one of the questions that we want to ask ourselves, because the thing is we're definitely going to go right up against this thing, the cosmic dark ages.
Yeah.
And the cosmic dark ages is going to take us, honestly, a bit of luck. Although I think over the whole sky, our luck is going to be pretty good, because, you're looking back to a time when the gas between the galaxies was actually opaque. It actually absorbed light. The cosmic dark ages isn't even a function of we just need to build a bigger and better telescope. That there actually was a time earlier in the universe, before about 200 million years after the Big Bang. The universe, the gas between the galaxies was absorbing light very well. And so we're hoping that what we see, and as you can see in this diagram, we hope it's kind of patchy.
Yeah.
Because what happened, is that eventually that gas got heated up and kind of blown away by giant stars forming, putting off lots of ultraviolet light. Giant black holes had big jets that went out, and they kind of cleared away all of this opaque light. It's called opaque gas.
Yeah.
So what we're hoping is that up against going deeper and deeper back in time. Eventually, you get back to a time when a lot of the starlight's being absorbed by this gas.
Yeah.
But right around a big cluster of stars or near a big black hole, something will blast through, and we'll be able to see in farther than we normally would have, and maybe even get a sense of what those first stars were like. And the first stars for me, that's kind of my big excitement, because I think they might have been very different than stars today. They might have been thousands of times the mass of the sun.
Yeah.
The formation might have been dominated by dark matter, bringing all kinds of stuff together even faster than it does. So, to me, that's the real thing: is are we going to get a glimpse into those dark ages?
These population 1A stars, possibly all made of kind of hydrogen and low levels of heavy elements, these kind of things.
Well, that's right. We call them population 3 stars.
Population 3.
So,
excuse me.
The other way. Yeah, that's right. So,
1A supernova, population
1A
3
supernova.
Stars, that's right. Yeah. Mixing up my astronomical terminology, but yes. That
well, of course, when 1A supernovae are going to be extremely important, because they're going to help us probe whether this dark energy thing really exists. So, this idea of the universe has expanded perhaps at different rates. This is something that if I were in graduate school, people would have just been like, "You're nuts." But we actually have real evidence now that there was sort of a change in the expansion rate of the universe about 5 billion years ago, and this is where this idea of dark energy comes from. We don't know that it's dark or energy. We know nothing about it. All we know is that something seems to be kind of wonky about how the universe expanded, and were there other times this happened? So those 1A supernovae are really important, and yes, we'll certainly be looking for those too.
So this seems to be the big takeaway from this image, is that if you can see further back in time to higher redshifts
in half a day,
in half a day, yes, correct, then you can get more of an idea how the universe evolved, because you're filling in those time periods, right? And then we can compare our models to what we actually see in the sky. They'll probably all be wrong in some way, and we can update them with more information about what we actually see when we go back to those earlier epochs. The amazing thing in this diagram is all of these distant red galaxies pop out that you can't even see on the Hubble diagram, right? And you mentioned that not only can we now see those with the ability to collect more light, the ability to see further into the infrared, but we can also take their spectra. So we can take their spectra essentially as a function of distance, as a function of time, and we can see how those stars, those abundances of elements in those stars change with time and change with I guess, position on the sky as well. So we can get so much information, almost a kind of roadmap of how stars changed over the age of the universe. Is that going too far, or is that?
Oh no, I mean that's the whole point, right? So I mean, what do galaxies look like 5 billion years ago? What do they look like 10 billion years ago? What do they look like 13 billion years ago? What were the first galaxies like? How are their shapes different? How do they change over time? I mean, the big galaxies like the one we live in, the Milky Way, we now understand that these things didn't exist in the early universe, that were the product of lots of smaller galaxies merging together.
Yeah.
So, the giant elliptical galaxies we see today, the big spirals, that's not what we see earlier in the universe. So we're going to figure out how something like the Milky Way forms, and how all these other galaxy forms. But like I said, I mean, this spectrum, I mean, Webb is a scientific discovery machine.
Look how clean it is.
Look how clean it is. And this it's again, I mean, so not only are we taking this beautiful image, but we're taking the spectrum at the same time. We're getting all of this information about what chemical elements are being formed, information about how far away these different galaxies are, right? I mean, one of the big results from this image is you could tell all these weird little smeared out galaxies were actually the same one in some cases, because they all had exactly the same spectrum.
Yes.
It was just like, bam, bam, bam. Those are the same ones, just smeared out by the lens. And so, it's the speed of it.
And usually I've seen people, I remember we talked about Erendel, they sort of look at the image and they say, I think that's part of that one. But now you don't have to, you just go spectrum,
bam.
yeah, bang, done. Thank you. Right.
And I'm sure Erendel is going to be one of the targets. I think it's in the first year's observations. I'm not entirely sure, but I know we're going to follow up on that. Yeah.
This diagram is like something you would put in a textbook to say this is what a spectrum should look like.
Yeah.
It's absurd. So that
where's the noise?
That's what I mean. Like where is it? It's like right, yeah. It's like, oh, we better add a little bit just so people think it's real. But okay, fine, whatever.
Yeah.
So that's the deep field, and it is truly is amazing. The second one, which I will admit that my image, the image that came out from you guys this morning was my favorite, was the Carina Nebula. So.
Okay. Yeah.
Yeah. No. Which one's your favorite? Which one are you going with?
Oh no. I'm just when we said second one, I was wondering if we were going in the same order we did today.
But we can go in any order that you like. I'm happy to go.
Yeah. So here's the Carina Nebula. It's my favorite thing to look at through a small telescope whenever I'm in the southern hemisphere. You can see those beautiful dark dust lanes even with a small telescope. It is a gorgeous nebula.
So this is a stellar nebula. And this is one of the largest and brightest nebulae in the sky, located about 7,600 light years away, as you correctly said, in the southern constellation of Carina. So this is essentially where stars are born, in huge clouds of gas and dust. And it also includes Eta Carinae, which is one of the most massive stars that we know of in the galaxy, 100 to 150 times more massive than the sun. So again, here with this image, we're kind of hitting another one of those main points, right? Stellar birth and death. We're interested in stellar birth. Is that why we're focusing on this nebula? And if we look at
absolutely right. I mean, so like I said, you got all the star birth going on there, and then one of the stars that formed recently is this big hulking thing. It's a binary star, and honestly, we're a little worried about this guy because this is one of the closest stars that's massive enough that it could produce what's called a gamma ray burst. I mean, it's even more than a supernova. And, if this star were to gamma ray burst and we were in the way of the jet that came out, it would kill us.
Wow.
So from 7,000 light years away. Yeah. So, I mean, this is one that we're keeping an eye on. And
have a look at that one for us and just see what's going on.
Yeah. I'm not kidding. I mean, the chance, of course, is small because these bursts come out in jets, and we'd have to be right, unfortunately, in the way of the jet. But all the way from that distance, it could kill us all.
Okay, good. That's brought us down to
don't lose sleep. Yeah,
exactly.
It's much more likely to be hit by a bus or something.
So we've seen this amazing nebula in Hubble images in the visible, but that doesn't tell us everything, because really what we want to do is see it in the infrared, which we see when we go to the Webb image, because we can see through these layers of gas and dust, and it's almost like pulling the curtains back and seeing all of these stars inside and what's going on inside those regions, isn't it? And the
Yeah,
detail that you can get.
The Hubble image is beautiful too, but you sort of see the sort of the front of this dust cloud.
Yeah.
And with the Webb image, the infrared, near infrared especially, has the ability to actually really go through the dust. And so all of a sudden there are these structures in there. There are these arcs and jets and weird mountain shapes and all of that. And inside there's all these new stars and planets forming, these entire solar systems. There are hundreds of stars in this image that we've never seen before.
Yeah.
So, I mean, some of the stars are actually in the background. They're not even part of the nebula. They're just so far away that their light came all the way through the nebula in the near infrared. But some of those sources are deeply embedded, dense parts of the cloud where there's a new star forming inside. And so, we basically are starting to have this kind of like, to use another term of light, X-ray vision, looking into the cloud, seeing all the swirls and what's going on, and here stars forming here, something's going on there. So, this is just like, for those of us that specialize in star formation, like you said, it's, the obscuring materials pulled aside, and now we get to go through and really see how the whole thing works.
So we can now sort of answer, we're not going to go into all of these questions, obviously, but these were some of the sort of sub-questions that Amber Strawn put up in one of her talks. All of these questions now we can start to get an idea of. How does that collapse of gas happen to create a star? Whereabouts in the nebula does that happen? What is the environment that has to exist for that to start to happen? We can start to get an idea of how the actual... We have a rough idea of how that happens, but where and why does it start? We can start getting a much better idea now that we can see through and peek through those curtains, as it were.
Oh, absolutely. I mean, so how does part of the star, how does part of the cloud decide to form giant stars like Eta Carinae, and how how does part of the cloud decide to form little ones, and how does the cloud decide to form like a binary system or a 3-star system, and over here we're forming stars that are kind of by themselves. I mean, people ask these questions as if we already know the answers, and we have a rough idea how star formation works. Yeah, okay, cloud collapses, gets hot, boom, star. But then they'll say, well,
that's about my level of knowledge as well, by the way.
But then they'll say, it's like, well, so how does the star know to form a big, how does the cloud know to form a big star versus a little star? It's like, that we don't know yet. And there's so many questions we have that I think just this one image, and again, a short image, didn't take long to make.
How long did this one take?
I don't know offhand, but I know that none of them took a long time. They wanted the data quickly, and so none of these were long.
That's actually one of the kind of most amazing and kind of scary things to me as well. How quickly this thing can operate. Yeah. We're on the edge of a quantum shift in our understanding of the universe, because it's just,
like I said, it's a machine. It's going to pump out discoveries.
It's absolutely ridiculous. So that's the Carina Nebula, which is incredibly beautiful. I will say it was my you said that you kept it to last.
Yeah.
It's so beautiful. It's fantastic, as well as showing that explicit science case of why it's so useful compared to the other images. So next one, WASP
96b.
WASP 96b. So WASP 96b, for people who are watching, is a giant exoplanet. It's a giant planet outside our solar system, and it's composed mainly of gas. So obviously this is an artist's impression, not a photograph. It's located 1,150 light years from Earth, and it orbits its star about once every 3.4 days. It's got half the mass of Jupiter, and it was discovered in 2014. So what's the deal with the WASPs?
Well, okay, so again, I think this was kind of a low-hanging fruit. They wanted to see how Webb did with what you said, transits, right? Yeah. So what happens is, if everything's just lined up perfectly, when a planet is orbiting around its star, it'll actually, to our perspective, move in front of the star, make a little tiny solar eclipse, and block out a little bit of light. Planets are so small that even a big telescope like Webb, or even bigger ones like the ground-based ones, we really can't resolve planets into actual little disks. Yeah. They're just too small compared to stars. So what we look for is this dip in the light. So the planet blocks out a little bit of light, and okay, there it goes. There's a planet. But the Webb is so sensitive that what we can do is that just as the planet is moving in front of the star, just as that happens, one of the last things that the light shines through is it shines through the atmosphere of the
This is
planet.
absolutely amazing, by the way.
Yeah.
This is ridiculous.
So the planet's moving in front of the star, and then about as it goes, as the eclipse begins, you see that starlight going through the edge of the planet and the atmosphere, and the chemicals that are in that atmosphere then absorb different sorts of light out of the starlight. And so here we have, bang, again, short exposure, nothing very difficult, water vapor. And so this is a hot planet. This is not liquid water. These are hot clouds. But they contain water vapor. I mean, not only that's interesting, that's cool, but again, it's meant to show you just how clean the data is. And I know in this case it looks a little wobbly, and there are data, there are error bars that you need to pay attention to. But the whole thing is you can see these structures in the spectrum that we know are the chemical signatures of water. And so for me, the next big step is this. Now that we know that we can do this quickly and well with a big gas giant planet. You better believe we're going to go after Earth-like planets.
Yeah,
so planets that are
people want TRAPPIST-1 straight away. Like they're like, go,
TRAPPIST-1 is one of the early targets. Yeah, absolutely. So and TRAPPIST-1, for those of you that may not know, has 7 Earth size and density planets, pretty close, well, very close into the star. So I mean, we'll have 7 Earth density, Earth size planets to target. And I mean, and they will probably have very different atmospheres. The ones that are closer in, they might have no atmosphere at all. They might be like Venus. The farther ones out might be frozen. They might be like Mars, but maybe there's going to be one that's just right. And I really do think, and of course this comes down to what the universe offers us. But we have the ability to say, and I think it'll happen the next year, that there is a planet out there that is the size, density, and temperature of Earth, and it has an atmosphere similar to Earth.
That is going to be one hell of a story when that happens, because that's kind of what we've been looking for all along with our Earth-centric hat on. This is honestly this was one of the coolest things that I saw from the presentation today, because the ability to do this tiny thing ring of atmosphere that's traveling in front of the star, and you've got this huge, basically lighthouse lamp behind shining stuff through. To be able to separate out that light that's going through the atmosphere from the general luminosity of the star is absolutely phenomenal, and Webb can do it. And if we look at the old sort of spectrum that was taken from WST, so I believe this was with with Hubble. It only went out to 1.8 micron, and it's quite fluffy, and there's quite large error bars. But if you go to the Webb,
the infrared,
the infrared, not only do you get out now to nearly 3 microns, also, as you correctly said, that the error bars, although they are something that you want to take account of, the structures are very, very clear.
There's no way those structures are random. That's the signature of water. And so the
is this a vibrational spectrum? I guess in the infrared is.
That's a good question. It probably is. So what that means is that the water molecule has modes that it vibrates in, and it can absorb infrared radiation, and the whole molecule begins to wobble in certain ways. So the reason that another reason infrared light is so good is that a lot of these vibrational modes of molecules and absorption modes of molecules happen in the infrared for things like water, oxygen, carbon dioxide.
And this is why we're worried for climate change, right? Because it captures all of this infrared that we're putting
so out. That's the thing, right? Yeah, exactly. So our atmosphere blocks all of that because it's very good at capturing infrared light. So you need to go above the atmosphere, and then you see these really nice chemical signatures for these molecules that are very important to life.
The one other, before I move on from this to the final two, the one other cool thing that was mentioned, I think it was it Jane or someone else who was talking about this image. They mentioned that there are probably clouds on this planet, and I didn't quite understand how they'd got that from the data, but they were essentially saying that we know some aspect of what the weather is like on this essentially huge planet very close to its sun. How did they get an idea that there are clouds on this planet?
Yeah, okay, that's an interesting question. So there was something about the Hubble spectrum, I remember, that there was the Hubble spectrum was very, very preliminary. And I think that maybe some of the lack of some of these molecules made them think that it was a clear sky, that there were not clouds. But now we're seeing things like water vapor that we assume are due to clouds. So it was a little bit of a look back to the Hubble spectrum, where it's like, well, we don't, maybe it's clear, but now it's like, that's probably cloud stuff. So
I see, that makes sense now. So it's bringing them both together. But this is truly amazing. Not only will we get some idea of what chemicals are there, maybe signatures of life, organics, which people are really interested. Right. But also, if we know what they're made of, we can start to understand where those building blocks came from. The pizza is here. Is that
That's
the
my pizza? Yeah.
Go get the pizza.
I'll be right back.
No worries. No worries.
This is an astronomer getting her pizza. All right.
Not a problem at all.
Hi there. Thank you. Thank you very much. All right.
What did you go with today?
I promised myself, I've been like not eating very much and not drinking. I promised myself a really nice pizza to myself and a bottle of wine tonight. So there goes the pizza in the oven.
You definitely deserve it after today. Yes. Especially
Absolutely.
With the hell they made you go through with the tech. God.
So anyway, back to the spectrum.
Right. So not only do we know what's in the atmosphere, we can maybe understand where those elements came from, and therefore learn a little bit about planetary formation as well, I guess.
Yeah. I mean, so there's a lot of stuff about where in a planetary disk forming planets do you find a lot of water?
Yeah.
There's controversy about where the Earth's water came from originally. Some people say there was always water here. Other people say that a lot of it was brought in later by collisions of asteroids and comets. I think one of the reasons we think that is that by and large, when we see other solar systems forming, and you see these other swirling disks of gas, the place where Earth is doesn't have a lot of these what they call volatile molecules, things that are kind of easy to evaporate. You sort of get that out by the orbit of like Jupiter and Saturn. That's when things start to cool off enough to get those things to condense and form ices that you could actually put into a planet. So, I think that, of course, we'll be looking at that, and then some people say, well, no, that's not right. I mean, the Earth always had water here. So there's a lot of information about how even our own planet formed that we don't know.
Yeah.
And, we hope that looking at thousands and thousands and thousands of examples of other worlds will help us piece together the answers about what happened here.
That's amazing stuff. When I was sort of researching for the chat with you, I came across this, which I'm sure you've seen, which is the Kepler orrery, which was showing the sort of distribution of or the variability, I guess, the diversity of exoplanets that we've discovered, and it's just ridiculous. How do we make sense of this? The only way we can make sense of it is getting thousands and thousands more and seeing if we can start to see patterns in why do they do this? What sort of environments did the certain ones form in? Are there, apply some AI to it or something, try and get some patterns as to why this is happening and come up with some models to explain it. It's like you said, people, I think, really think we have a good handle on how these planets form, but there's still so many open questions, right? Why are they so different, and what causes that to happen? Is it different elements? Is it different environments? Is it different rates of things happening? What is going on to create this ridiculous level of diversity? We don't quite know yet in planetary formation.
Yeah, well, I mean, and it's funny, you mentioned artificial intelligence. This is something we actually do a lot of. We use machine learning and other AI stuff because, so right now there are about 5,000 confirmed exoplanets. There are about 10,000 that we're still following up on. And the reason you have to follow up on is you have to make sure you see that eclipse come back again and again and again.
Yeah.
Because, if you just see a dark spot go across a star once, I mean, that could be like a sunspot.
This was the problem with the one in the other galaxy that I remember. They've only seen one transit.
Yeah,
so people are
exactly.
Really?
So, I mean, you really have to make sure that these things come back. And of course, in the case of things like TRAPPIST-1, I mean, here's where machine learning, the TRAPPIST-1 planets are so close together, they actually change each other's orbit every time they orbit. They actually tug and pull on each other. And the orbits of the planets shift. I mean, in some cases by up to a minute every time they go around. And so talk about fun with Fourier transforms, because it turns out that if you see all of these planets and they're all transiting, but then their orbits are changing.
You're probably like, what the hell is going on here? Like,
but you can work out their masses. Yeah. Think about that. Yeah. You can work out using Einstein's equations how much they're changing each other and what distance, and you can figure out how massive they are. Wow. Again, fun with Fourier transforms. Yay.
Always, I remember my physics professor said, if I could only teach you one aspect of physics, it would be Fourier transforms. He was obsessed with the things, and they come up in so much.
Well, they come up everywhere.
Every single place.
Yeah, I mean, from trying to, just seeing those event horizons, those dark spots around by the black hole, to finding planets. If you can do your Fourier transforms, you're doing well.
You're halfway there. So we're on to the last two, because I want to let you get to that pizza. Please tuck in while we're going, because
I put it in the
we're in the oven, right?
So it's all good. Yeah.
How long is it going to be? I'll make sure we're done by the time it's ready.
Oh, fine.
All right. Okay, good. The penultimate one was the Southern Ring Nebula. So here we've got it invisible. Mm-hmm. And I believe near infrared from Hubble. And then if we go to the beautiful Webb image that we saw today, we can see it much more clearly and much more detail. So what have we got going on here with the Southern Ring Nebula? What is that?
Yeah, so it's a beautiful bubble that's being blown by a dying star. So there's actually a binary star in there, and one of the stars is today a white dwarf, which is basically just a dead, burnt out core of the star, still cooling off. No more nuclear reactions. It's just a big ball of inert material that is still very hot, but it's just cooling off. But in the time before it became this white dwarf, it basically lost all of its outer layers of gas, and that the star unraveled itself back into space. And then this is the kind of gentle star death that is in store for the sun. Instead of like blowing up violently, you just sort of unravel. And there's lots of different eras where the star expands and contracts and gets bloated and then comes back in. And so there's this story that as these different layers drift out into space, there's this whole story in there about how the star died.
Yeah.
And of course, a lot of that gas, as it goes away from the star, is cooling down. It's no longer glowing in visible light. So in infrared, where you can image something that's still warm, as this gas is, then you can see these structures extend way farther away from where we just saw them with Hubble. And once again, we'll see more detail when we do a longer exposure of this. So there's the innermost ring area that you can see in the Webb images as well. Yeah. But now you're beginning to see everything lit up, and of all of this stuff, going away. And there's spirals, and there's material, and there's turbulence, and there's shocks as the gas hits different layers. And so, once again, looking at this, in there is the story of how this star died, and how the entire process of star death works. I mean, I'm sure it's a little different for every star, but this is an example of how this system died. And the nice thing about the mid-infrared image, which is the one that's looks a little bit fuzzier, but kind of, is you can actually see the binary star really clearly. So, although a white dwarf is so small, it's only about the size of the Earth, that even though it's very hot, it doesn't put off a lot of visible light. It's a tiny thing, but it's putting off plenty of heat. It's a hot thing.
Yeah.
And so by the time you get out to the mid-infrared, you really see the glow of that hot little dead core of that star.
So the beautiful thing about this is, again, you're hitting one of those key points. We're talking about star death. So we've got star formation in the stellar nurseries. We're going through that process. We get to star death, and we're covering all those bases.
The alpha and omega of stars. There we go.
Exactly. Yeah. And we're open for business on both. And not only that, but as you said, what's beautiful about this is you can see with the different images in the different wavelengths that you can see such different stuff. There's so much information in just having those two instruments look at the same thing. You can't even make out the binary system in the first one. But then when you go to the mid-infrared, there it is, this dusty partner that you can then make out. So there's just so much information you can get by just looking in different wavelengths, right?
Absolutely. I mean that's why we build these different telescopes. And in the case of Webb, over and over again, I mean, why do you need to put this huge thing in space? This light doesn't get through our atmosphere. There's no way to see it here. So, I mean, if you want to study mid-infrared and you want to see how these stars unravel, and mid-infrared is particularly good at showing you where the warm material is around the star, there's no other way to get it. You have to go up above the atmosphere to get it.
This is just absolutely amazing. Like the amount of knowledge we're going to get from this. People are going to be looking at this for years, just like Hubble has been for 30 years. This is now going to be Webb.
You're watching it live, rewriting the textbooks as we speak.
People were saying this morning that they just kind of had that realization that we're watching history, scientific history, unravel right in front of our eyes. This is not, one paper and then we're done. This is a new frontier, a real shift in our ability to understand where we come from, where we're going, and all of the things that are in the universe around us. It really, really is that bigger.
And I'm going to keep saying it again. This is, I mean, and I don't mean this in a bad way, but this is quick and dirty. This is what we took quickly and got out to the public
and
as quickly as we could.
That's what's scaring me, that it's this good with quick and dirty. It's absolutely absurd. Absolutely absurd. Really, It really is. So let's get on to the final one, so that you can then go and have your pizza and wine. So that's the Southern Ring Nebula. Stephan's Quintet. Well, it is a quartet because I believe this one is actually in the foreground, but.
Yeah, but I know it's called Stephan's Quintet. I just misspoke.
Right. Okay, good. Right, so this is Stephan's Quintet. So this is about 290 million light years away, and it's located in the constellation of Pegasus, just like Atlantis in Stargate. So that's good. It's noticeable for being the first compact galaxy group ever discovered in 1877. So there's a lot of history to this thing. 4 of the 5 galaxies are within the Quintet. It's always good to learn. I can teach you something as well. I'm happy to. I looked in a kind of cosmic dance with repeated close encounters. And this one at the top left is much closer to us. So you can kind of make out more of the stars as kind of point sources. But when you superimpose it on the sky, it sort of looks like a quintet. So I guess the idea here. And let's have a look at the beautiful image from Webb here.
Da, da, da.
It's so cool. I guess the idea here is, again, we're hitting one of these key ideas of how do galaxies assemble themselves? How do they interact with one another? How over the evolution of the universe, as you mentioned earlier when we were talking, did we get to these spiral galaxies like we have, or the Milky Way that we live in? Why do they not look like the ones that we see in the earlier universe? How have they interacted, merged, come together, interacted with their environments to create the galaxies that we see today? We don't really know.
I mean, our whole view of galaxies is really kind of skewed by the way basically light works, because, when you think about a spiral galaxy, there are these gorgeous spiral arms. Well, I mean, it turns out there's nothing really physically, they're not physical structures. Well, what's happening is that there's a burst of star formation as these sort of waves of density move around the galaxy. And the way I always sort of, the classic way to talk about it is stars all orbit the galaxy. They're all going around in their own orbits. Right now the sun is circling around the center of the Milky Way at 500,000 miles an hour. The spiral arms, we actually move in and out of them. Right. I mean, our orbit is not really affected by that. But what happens is that there's just a region of the galaxy where things kind of pile up a little bit, like a car going through a traffic jam. So the sun, when you're driving through a traffic jam, you're still going forward. You're still going the same direction. You're still orbiting around the galaxy, but you get to a place where things are just a bit denser, and then you move out again, hopefully. And so those density waves set off a burst of star formation. And so these spiral arms, the reason they look so beautiful and lit up in blue is just because there's new hot young stars. But if you actually count the number of stars in a spiral arm and between the spiral arm, it's almost the same, because these hot blue stars put out lots of blue light. They're really hot and bright. They don't live very long. They live a couple million years. And the sun goes around the around the galaxy once every 240 million years or so. And so really hot, bright young stars don't even have time to move out of the spiral arm. There's like, bam, here I am, and they die. And so, the underlying structure of a galaxy isn't really spiral shaped. Instead, there's all of these interesting, you see here sort of this scaffolding of dust.
Yeah.
So you're not looking at starlight anymore. You're looking, well, I mean, in some cases you are, but you're looking at the underlying material and what it's doing. It's like, don't be fooled by the spiral arms. This is really what's going on. And so we think that spiral arms and in fact, star forming regions, like that lights them up, they probably happen when galaxies tug on each other gravitationally. Because galaxies occur in clusters. They merge together. That's how you get big galaxies like the Milky Way. The early universe does not have big spiral galaxies like the Milky Way. Instead you have these smaller galaxies that come together to form the big galaxies. And I mean, this is one of the big deals. How do galaxies change and evolve over time? So here we see at least 4 of these galaxies in the quintet, tugging, pulling, creating star formation, changing the way the galaxies work. And I know in one case, feeding a giant black hole.
Well, this is the kind of final bit I wanted to come on this. So not only did we get this beautiful idea of these interactions between the galaxies, and I guess if we have huge samples that we can look at all over the galaxy, or all over the universe, we'll be able to get an idea of how these interactions happen and how they change with time and how they feed forward and put those into our models again. But we were also able, with these images, to take another spectrum of not only the composition of the gas around one of these black holes. So maybe we could be able to, thinking about what we did earlier, maybe we would even be able to date it if we looked at, separate galaxies from different eras. But we can talk about that. Not only did we find out what was in the dust around this and gas around this black hole, but also how quickly it was moving from the spectral data from Webb. So the amount of information that we can find out about these distant galaxies from this one machine is absolutely stunning. We know that black hole is there. We know how fast the material is going around it, and we know exactly the components that are inside that dust. It's really is mind blowing.
Yeah, and so when you see how fast stuff is going around it, you can start to estimate its mass.
Yeah.
You can start to see how the mass of these black holes change over time. I mean, one of the big challenges in modern astronomy is we see these giant black holes so far back in time when the universe was less than 1 billion years old. And they're already like millions or billions of times the mass of the sun. So I mean, these things had to form quickly.
Yeah.
And I mean, is that really what a galaxy is? Is a galaxy kind of the schmutz that gets left over when you're forming a big black hole?
Yeah.
And we all are orbiting the giant black hole at the middle of the Milky Way. Every big galaxy seems to have a big, massive, supermassive black hole in the middle. So, how big are these black holes? How do they grow? How do young galaxies compare to galaxies today? Yep, we got it. We got 50 scientific papers out of like one image alone. It's just like, go.
I remember somebody saying that if the universe is optimized for anything, it's for the creation of black holes. So
from the small to the large, right? I mean, you've got the tiny black holes that are formed by cosmic rays in our atmosphere, and you've got supermassive black holes that are formed somehow very early in the universe. So we'll figure all that out.
Absolutely amazing. I want to let you get to your pizza, but that was a really beautiful. Okay. That was a really beautiful breakdown of those 5 images. Thank you so much for taking the time to go through that with me. That was absolutely brilliant. I'm going to put the deep field up just while we come to an end.
It's a lovely one.
I want to ask you just before we finish, what's your